Okay, to finish up the second derivative test discussion, what we need to be able to do is somehow work into this equation the idea that what we're actually getting are the gradient vectors, and you can see that there's actually nowhere, not in the picture, not in the algebra, is it there. Just a reminder about what's doing. We are plugging in the input vector delta x delta y. That's the red one. Remember, that's the one we don't draw. And then we're getting a vector out, which is actually the gradient vector. And the way linear transformations work is that we're taking this matrix that we don't know yet. We are multiplying by the vector delta x delta y, and the answer we're getting is the gradient at q. The gradient at q. And so if we're going to do anything at all, what we need to do is focus on this piece, which we haven't even started discussing yet. And there's a really, really cool way that we're going to address that. We are going to use linear approximations. We're going to use, for example, the fact that near AB, a function, say, let's call it g of xy, is, well, it's approximately equal to, that's better, is approximately equal to g of AB plus gx at AB times x minus a plus gy at AB times y minus b. Now what we're going to be doing is lots of different things. We want the notation here to match up with the notation that we use in the second derivative test. For example, the point we're really interested is P, and so we're going to call the point ABP. The number we want to plug in is Q, so we're going to call Q the point xy. We know that x minus a is actually just delta x. It's a change in x values. I'm going to call y minus b delta y. And so this actually starts to look a lot more what I want to look like. I can rewrite this as g of q is approximately equal to g of p plus gx at p times delta x plus gy at p. It's delta x, this is delta y. So all I did was write down the formula for linear approximation again. Now, why did I do that? Well, what I want to do is estimate, say, for example, the partial derivative of f at x at q. In other words, what I want to do is take this formula for the linear approximation and plug in fx for q. In other words, I'm sorry, it's for g. Wherever I see a g, I'm going to put fx. So for example, I can write down that fx at q is approximately equal to, putting in an fx, I have fx at p. Now the next one might be a little confusing. I know that the g right there is fx, but that's just the g. There's another x there, so that's going to be fxx at p times delta x. Now g is fx, but there's another y there, so that's y. So they get p delta y like that. And I want to do the same thing for fy. So I'm now going to plug in fy for q. I keep saying q. Fy for g. So in this formula up here, wherever I see a g now, I'm going to put an fy. So I'm going to say fy at q is approximately equal to fy at p plus, let's see here, that's fy, and there's another x, so that's at p delta x plus g is fy, and there's another y there, at p times delta y. Now that looks way more complicated than we're used to looking at. However, remember that all of this conversation starts with saying P is a critical point. And since we want to use the second derivative test, it cannot be a critical point where the derivatives were not defined. It had to be a place where the partial derivatives were 0. In other words, saying that p is a critical point and that there are second derivatives involved is the same thing as saying fxp had to be 0. That's usually how we find it, right? We take the partial derivative with respect to x and we set it equal to 0. Same thing with respect to y. We get fy of p equals 0 like that. Now that says, in this great big huge mess right here, I can cross off that, and I can cross off that. And I'm going to write those two equations again at the top. It's going to take a minute. I think it'll be worth the time. So what I'm going to do is I'm going to write fx at q. Remember, we're trying to make a gradient out of this, right? In fact, so I'm going to write it like a vector. I'm going to say fx at q, fy at q is equal to this whole mess in place of fxq is a really good close estimate, and this whole mess for fy at q. So here we go. Right, so in the top row, I'm going to get fxx at p, delta p, plus this is fxx, this is fxy at p times, let's see, this is delta y, this is delta x, then down here I have fyx at p times delta x, and then I have fyy at p delta y. And one of the reasons they make us do things like multiply matrices times vectors when so many times technology does it better is that we can look at this and recognize this as being a matrix times a vector. In fact, if I pull out the variables, which is just delta x, delta y, and write the coefficient matrix, what I'm going to get is fxx at p, and then fxy at p, and then fyx at p, and then fyy at p times delta x, delta y. And what do we have? We say if we were looking for the linear transformation that draws the gradient vectors, we are looking for a matrix full of constants. Well, that's this one right here, times the vector delta x, delta y. That tells us that the matrix we've been looking for, this is ABCD. Why? Because the gradient vectors near a critical point all look like a linear transformation, and we just found the matrix for that linear transformation. And it's the vector, it's the matrix that's full of the second partial derivatives. That just about finishes the second derivative test. We'll try to write up all the conclusions tomorrow. One final note, this sort of matrix that's full of all the second partials in just this order is called the Hessian matrix. Its derivative is called the Hessian determinant. And that's all for now. But at least we now have conclusions involving the second derivatives and determinants.